Today we have Sourav Chatterjee from Stanford, and this year a member at the Institute for Advanced Study. And he's going to talk about chaos in lattice spin glasses and, very interestingly, some questions for analysts.
Okay, thank you, Camilo and Bjorn, for the invitation. It's a great pleasure to be here at the Institute in general, and especially giving a talk at the analysis seminar. So spin glasses, these are actual physical materials. So magnetic materials with some strange glassy properties. So I'll not go into the physics because I have quite a bit to say in terms of the math, so I'll not go too much into this. And this was possibly the first model. This was by Edwards and Anderson in 1975. So this is the model that I will talk about. This is the lattice spin glass model, the very simplest model you can think of lattice spin glass. So this is a spin glass model on a lattice. And this was a simpler version. So I'll tell you why I'm putting the quotes here. So simpler version, this was soon after, in the same year, Sherrington and Kirkpatrick also 1975, and this is the mean field model. So if you're not familiar with statistical mechanics, a lattice model or short-range model is where you have particles which interact only with neighboring particles, so close neighborhoods. So that's a more realistic scenario. And a mean field model is a simplification of this model where all particles interact with all others on an equal strength. And so that often simplifies the theory. So in the case of lattice spin, in the case of spin glasses, this didn't really simplify a lot. So this SK model, as it is called, led to this very rich branch of physics and mathematics, the analysis of the SK model. So this was by Giorgio Parisi, 1979-80. So this was the broken replica method. And this was a revolutionary idea, which led to a lot of developments. Finally, getting Parisi the Nobel Prize in 2021. And on the math side, so Parisi's formula, the formulas and conjectures and other conjectures have largely been verified by mathematicians now, but completely different methods because the broken replica method is, as it stands, is far beyond anything that you would hope to be able to make rigorous. It involves, groups of size 0, matrices of size 0, and etc. And so verified by mathematicians, and it took a long time. So there's this famous, telegrams proof of the Parisi formula. In 2006, and Panchenko's proof of ultrametricity. So these were all conjectured by Parisi, and this is 2011, I think. And so these are landmark works on the math side, and there's still work ongoing to settle the other conjectures. But this is all for the simplified model, okay? The model which was supposed to be more tractable than the Edwards-Anderson model, okay? On the short range side, so the Edwards-Anderson model, almost no, significant progress. So this has remained almost completely intractable, and even on the physics side, there are disagreements. Okay. So even on the physics side, there are significant disagreements between various groups of physics, and it's not clear what is the true picture. So let me now introduce this model and tell you what I was able to prove last year. So what's the model? So here's the model. So let's say you have a region 0, 1 up to L to the D. So you have a box in a lattice, and you have spins plus minus 1 at each site. So a configuration sigma of spins belongs to minus 1, 1 the lambda. Okay. So on each site you have a spin, and you have this. You have a configuration. So now what the model does, as in any model in statistical physics, the model assigns a probability measure on the space of configurations. Okay. So it says that certain configurations are more likely than others. And as we say in probability, that you pick a configuration according to a probability measure. So it defines a probability measure, and the goal is to understand the behavior of a random configuration drawn from this probability measure. So what's the probability measure? So the probability of a configuration sigma is proportional to e to the power minus beta times the Hamiltonian, where beta is 1 over the temperature. E is the temperature. So this is the usual Boltzmann framework. So you have this temperature, and h of sigma, this is the main thing. So h is the Hamiltonian. Okay. And so what is the Hamiltonian in this model? Okay, so the Hamiltonian here, the energy, so this is the energy of a configuration sigma, is given by minus sum over all neighboring pairs ij and E, where E is a set of nearest neighbor edges of lambda, or Jij, sigma I, sigma j, where these are numbers. I'll tell you where these numbers are coming from. So I'll tell you what these numbers are coming from, but okay, so there is a minus here and that minus. That's the usual physics convention. You put a minus here and a minus, two minuses cancel out. So you have this energy function, and you want to define a probability measure which assigns a probability on these configurations. And the ground state is any sigma that minimizes h of sigma. Okay. So any configuration that minimizes the energy is called a ground state. A ground state is an energy minimizing configuration.
One question. So
Yeah.
when you say nearest neighbor, you mean that, I mean, apart from the boundary which you don't care, the usual element has exactly to the neighbor?
Yes. So those are the nearest neighbor edges. And okay, so the main thing is about these constants, where they're coming from. But suppose, the constants were all one. The GIJs are all one. That's called the Ising model. And the Ising model, the ground state is any sigma where the coordinates are all equal. So they're all +1 or all -1. That's the one. Those are the only two configurations which minimize the energy for the Ising model. The GIJs are all one. Okay. So, but for the Edwards-Anderson model, the GIJs are defined in a slightly strange way. So in the Edwards-Anderson model, GIJ are IID random variables. So that H itself is a random function. So this is, as it stands, it's just a function on, it's a very simple, quadratic function on the configuration space. But as soon as you declare the GIs are random, this becomes a random function. This is now a random function, and the ground state is now any configuration that minimizes this random function. So the ground state is also random. Okay. Any questions so far?
Yes, you typically want to make the JIJs have zero mean, right?
Yes, so I'm coming to that. So IID random variables, and so moreover, in the Edwards-Anderson model, we take GIJs IID with mean zero. So mean zero probabilistic terminology just means that expected value of GIJ is zero. So in this talk, we will take GIJs to be IID normal 0, 1. So this is a standard Gaussian distribution, which has probability density, 1/√2 pi e to the minus x squared over 2. There's a familiar probability density function of a standard normal. And we take GIJs to be IID standard normal. That's a common choice for these GIJs. And then you try to understand, what do the ground states look like? So it becomes, so if the GIJs are all of the same sign, they don't have to be all equal to 1. Suppose they're all positive, then the ground states must be configurations where the spins are all the same. But as soon as they're allowed to have both plus and minus signs, it becomes a non-trivial problem, to figure out, and it's actually an NP hard problem in dimensions 3 and higher to figure out the ground states. Okay. So a conjecture about the ground state is from a long time ago, is the conjecture of chaos in the ground state. So chaos, so chaotic nature of the ground state. Okay, so this was conjectured by Fisher and Huse in 1986, and also by Bray and Moore in 1987. Okay, that the ground state is chaotic with respect to small perturbations with the disorders. I'll make clear what that means in a minute. So what it means, roughly speaking, is that if you take these GIJs, if they can be both positive or negative, let's say IID normal 0, 1, and you perturb the environment a little bit in a specific scheme that I'm going to tell you, but it's supposed to be true in broader generality, then the ground state changes drastically. A small perturbation of the disorder changes the ground state drastically, and the reason that was given, and now there is, due to this, so this is what I'm going to prove, and due to the proof of this chaotic nature, it now follows also that there are many near ground states, near optimal, and states that are nearly minimizing the energy, which are very different from the ground state. So that's a typical feature of spin glasses, that you have many states which are almost optimum, but quite different from the actual global optimum. And so that's so that was the intuition behind this conjecture. But as we'll see that the proof doesn't follow from this intuition, because we don't really know how to make that, make sense of that intuition or make a proof without first proving chaos. So at least as far as I know, maybe there is a different way to do it, but I don't know a different way to prove that there are many near optimal states. Okay, so what is the precise definition? Suppose we replace Gij by Gij plus an epsilon times Kij, where Kij are independent normal 0, 1 and variables. So we take a small perturbation of each Gij, you take an epsilon perturbation, you take each of these random variables, and then plus some small epsilon times another Gaussian. So you replace that. And there are other ways of doing perturbation. This is just one way. Okay. Let sigma prime be, so sigma prime hat be the new ground state. So when I'm saying the ground state, okay, as I said, I did not prove that it's unique, but it's not hard to prove that if the GIs are all Gaussian and you're considering a finite box, there are just two ground states. There is a ground state, and if you flip all the spins, the negative of everything is also a ground state. Okay, and those are the only two, and they're very unique. So with probability 1, that happens. So sigma prime be the new ground state, and sigma hat be the old ground state. Okay. So then, you take as a measure of how similar they are, sigma I prime. This is called the overlap between the spins. So these are all plus minus valued, and if they were exactly the same, this would be 1. Okay. So this is close to 0 with high probability for small epsilon. So again, this is not completely precise. I'll make this more precise. So this says that you can choose. So small here means that epsilon is some function of L which goes to 0 as L goes to infinity. So you can choose epsilon decaying with the size of the box, so that this overlap, so again, close to 0 means that the difference between the size of this is less than something, again, that goes to 0 with as L goes to infinity, the high probability means that the probability tends to 1. Okay, so probability, so if the box is large, then you can choose an epsilon, which is very small, depending on the size of the box, so that these two ground states that you obtain, their overlap is very small with probability very close to 1, okay, as the box size goes to infinity. So this is, this should be hats here. This is one notion of chaos, and I can prove a version of this. Here is the theorem.
You say with high probability, you mean that the first Jij are considered fixed and we are moving only Kij, or we are moving everything?
So you have Gijs and Kijs given to you, and you're taking expectation over everything. Okay. Yeah. So
is it important, the boundary condition, whether you take it periodic or?
no, it's not important. So right now I'm taking free boundary condition. So I'm not putting anything, but it's not important. So in the paper, you'll see, all boundary conditions are. You need slight modifications of the proof for different boundary conditions, but it generally works out. So here is the theorem that, the expected value of this overlap squared is bounded above by, let's see, constant over so it was constant over L times epsilon squared, I think. Yeah. So in general dimension, so it's an arbitrary. It's actually, I think it improves, it becomes to the power D or something. So anyway, the main thing is that if epsilon is much bigger than 1 over root L, then the left-hand side is close to 0. So the expected value of the overlap squared, and if the expected value of the square of random variable is small, then the random variable is small at high probability. You can easily prove that. So yeah, so I think this is right. And you get improvements as you go in higher dimensions, but this I think is generally true in all dimensions. So this is what I will now prove, and okay. Approaches. Any questions about?
So this actually settles the conjecture, right?
Yeah.
If instead of taking this perturbation, you just take to one side and re-randomize it completely?
Yeah, so that's a different perturbation where you choose a small fraction of sites and re-randomize it completely. And I have a theorem for that also. So
one is not enough.
No, 1 is not enough.
You have to take a proportion.
You have to, so again, the proportion has to be at least 1 over L. So if the proportion of sites that you re-randomize is bigger than 1 over L, and that is somehow equivalent to choosing this epsilon to be like much bigger than 1 over root L in some ways. So then you can prove, and much of the proof goes through similarly. There are some steps which are.
If you just replace 1, you know that it's not chaotic, or just you cannot prove that it's chaotic?
I cannot prove. Okay. Yeah,
it could be chaotic.
It could be. So actually, that's a very good question. So essentially, so there are these. I said there are these competing pictures of what happens, and if Paris's picture is true, then replacing 1 should make it somewhat chaotic. It should have an effect kind of everywhere, replacing 1. We are far. And so even, I said a fraction 1 over L has to replace, but it's probably can be made better. So I don't know. These are. So we'll come to, in the abstract, I said, some questions, and we'll see how the proof goes, and we'll see, what more can be done. And, in some sense, what I did is very basic, and probably there is a much better refinement of the whole thing. Let's see how to go forward. Okay. And it's a general scheme, you can consider other random functions or, and ask the same question that, if you slightly perturb the initial conditions or slightly perturb the function, does the optimizer change drastically? And, it's the same question. So let's see. So the first step is to just expand out this thing. So this is it's the average overall sites, sum overall I and j, expected value of sigma I hat, sigma j hat, sigma I prime hat, sigma j prime hat. And so it's an average overall at I and j. So it suffices to show that for typical ij in lambda, this is small. So actually what we'll end up showing is that this is less than or equal to some constant over the distance between I and j times epsilon squared. Okay. So this will suffice, because for typical I and j, the distance is of order L, and then if we can prove a bound like this, we'll be able to get a bound like that over there, okay, because that's the average. So actually, we'll see how to do a quantitative bound given I and j, two sites on the box, in the box. And whenever this epsilon perturbation that we're putting in, epsilon is much bigger than 1 over the square root of the distance between sites, this expectation is close to 0. So note that this is a random variable which is either plus or minus 1. And the expectation of such a random variable is close to 0. It means that it's plus or minus 1 at approximately equal probability, which means that the relative orientation of the spins at I and j before and after the perturbation are sort of independent. So if one is plus 1, you cannot say the other is also likely to be plus 1. So they are, they're sort of independent. Okay, so how do we prove this statement? Okay, so it's particularly easy in 1D. So I'll tell you, why. Because in 1D you can exactly write down the solution. So just for simplicity, suppose. So here our state space lambda is 0, 1. The L, just this L spins, and suppose we impose the boundary condition that sigma 0 is 1. The spin at site 0 is 1. And this was already done in the paper of Bray and Moore, 40 years ago. So then you can explicitly write down sigma I hat is a sine of G01, sine of G12, all the way up to sine of Gi minus 1, comma I. Okay. So it's just the product of the signs, and that gives you the, energy minimizing state. And, it's easy to verify, because if you multiply sigma I hat times sigma I plus 1 hat, you just get the sine of Gii plus 1. And if you multiply that by Gii plus 1, you get the absolute value. And that minimizes the energy. So you see why this is chaotic, because a typical spin is like a product of L independent signs. And so if you just perturb a small fraction of the GIJs, give a small perturbation to the GIJs, a small fraction is going to change sign, but a large number, it could be a large number of them. So if epsilon is much bigger than 1 over L. So you'll get a large number of sign changes, and therefore the end result will become unpredictable, even if you're given the original configuration. So roughly speaking, that's the idea. However, this no longer applies in higher dimensions because you don't have such a formula. In fact, there cannot be such a formula, because of the NP-hard nature of the problem. So in D2 or more, there is no such formula. So what can you do? How do you approach this problem? Because there's no such formula, no way you can get a handle on this thing. So you just go ahead and try to do, that's where the analysis comes in, try to do some analysis. So let's see. So just to refresh your memory, recall the Hermite polynomials. So Hn of x is -1 to the n over root n factorial e to the x squared over 2 dn dx n over e to the minus x squared. And these are polynomials for n equals 0, 1, 2, and so on. So the first few are h0x is 1, h1x is x, h2x is x squared minus 1 over root 2, and so on. Okay. So the hnx is a polynomial of degree n. You can check that it's a polynomial of degree n. And you have these Hermite polynomials. Now, what are they good for? So one of the nice properties of the Hermite polynomials is the following. So let gamma be the standard Gaussian measure on R. Let gamma be the standard Gaussian measure on R. Then these Hermite polynomials, Hn, form an orthonormal basis of L2 gamma. So just, I wrote this down a little while ago. So what is the standard Gaussian measure? So this is 1 over root 2 pi e to the minus x squared over 2 dx. Okay. So if you take the standard Gaussian measure, it defines an L2 space, and the Hermite polynomials form a complete, orthonormal basis, form a complete orthonormal basis of this Hilbert space. Okay. And the square root n factorial is just to make them, have norm 1. So that's nice. So in particular, what this means, is that any L2 function fx of a normal 0, 1 random variable x can be expanded as fx equals sum over n equals 0 to infinity f hat n times hn of x, where f hat n, the coefficient, is just given by the expected value of fx hn of x, where this sum means that it's the L2 limit of partial sums. This is an L2 space, okay? And the order of summation doesn't matter. And so it's just, writing this thing in the Hilbert space. So this is the inner product of, so when you take the expectation of the product of these two functions, just the inner product with respect to the L2 gamma. And these are the Fourier coefficients, and you have this expansion. So any L2 function has an expansion like this. Okay. So let's see how this is useful. Okay, so now let's say you have not one Gaussian variable, but many Gaussian variables. Suppose you have x1 to xn IID normal 0, 1, and you want to write a function of x1 to xn. So what's the basis of, so gamma n is the n-fold product of gamma. So this is the standard Gaussian measure on r to the n. So you have a standard Gaussian measure on r to the n, and you want the basis of that. So what's an orthonormal basis? So now the indexing set is, instead of the non-negative integers, you take z, oh, I shouldn't use n, I'm using n here. So let's say you put x1 to xd, for instance. So this is d-dimensional Gaussian. So you have z plus the d tuples of non-negative integers. So z plus here is non-negative integers. And you define the multivariate Hermite polynomial Hn of x1 to xn, x1 to xd. So multivariate Hermite polynomial as just the product of univariate Hermite polynomials. Hn1 x1, Hn2 x2, Hn dxd. So these form a complete orthonormal basis of L to gamma to the d. So again, so instead of this here, you now have x equal to xn can be represented like this, where n now goes from z plus the d, and the rest is same. Any questions about this? So this is just, you have any L2 function of d independent Gaussian random variables. These can be represented in this infinite series sum, where again this side is converging in L2 to the limit, and the order of summation is irrelevant, and these Fourier coefficients are given by just that. And now x is a d-dimensional vector. And these are multivariate Hermite polynomials. The indices are d tuples of non-negative integers, and each polynomial is a product of, d univariate polynomials applied one to each coordinate. Questions about this? Okay, so this is all nice formalism. How can this be useful? This is so general so far. So let's get back to our problem. Okay. Okay, so we have our problem. Lambda is 0, 1 up to L to the D, and we have Jij or IID normal 0, 1, or let me write JKL for the time being for a reason, where KL are in E. So this is a set of edges of lambda. Okay. And you fix I and j in lambda. Okay, fix some I and j in lambda. Fix some I and j in lambda. Consider sigma I, sigma j, sigma hat I, sigma hat j, the product of the ground state spins at I and j, as a function phi j of the couplings. This is the whole collection of couplings, JKL. So once somebody gives you all the couplings, there is a unique ground state up to a universal sign change, so sigma minus sigma, but this is well defined. You take the product of the spins at two sides, that's well defined. this is a well-defined function, but it's a very complicated function of all these couplings. Okay, but it's a plus minus one valued function. So the value is just plus or minus one, but it depends on all these couplings, and you get a function. Okay. Okay, so we'll try to understand the Fourier coefficients of this function. Okay. So how do you expand this function? Phi of j, you expand it now as sum over all n in z plus to the e. So an index is now a couple, a tuple of non-negative integers, one attached to each edge, because there's one Gaussian random variable on each edge. And you take the Fourier coefficient phi hat n times hn of j, where phi hat n is the expected value of phi j times hn of j. Okay, so you have all these Gaussian variables, and phi j is given this whole bunch of Gaussian variables. You're producing a ground state, and you're looking at the product of the spins at sites I and j. I and j are fixed. Okay, you're fixing two sites, and your function of your function of these couplings, and of course you can always expand it. And this is, since it's plus or minus one valued, it's obviously in L2. So you can expand it in this multivariate Hermite polynomial series, where the nth coefficient is given by this product of expectation of this product. Okay, and n is now running over this set, one non-negative integer attached to each edge. Okay, so take a look and let me know if this is all clear.
What kind of regularity does it have? Is it, you have to check.
Yeah, so
It's obviously measurable.
yeah, this is measurable, and yeah, so I'm not.
But it's supposed to be quite rough, right? Or
So the thing is, the value is always one or minus one, and these are only finitely many Gaussians, so it's a finite dimensional space. You have a large box, but the box is finite. Okay. And so does the Zoom actually show only the middle two boards, or their boards?
Oh, yeah, if there's no person operating it, yes.
Okay.
But typically there's somebody operating it, so I don't know about that.
Okay.
I mean, they didn't tell me that.
Okay, so I'll stick to this board.
Yeah.
Okay, so anyway, the main thing is here. So you will have this, a large dimensional space, and on some regions you'll have plus one, the other regions you have minus one, and it will. I'm guessing it would break up into sort of polygonal regions where it's plus or minus one, and the chaotic nature indicates that it will be very rough. It will be, there'll be sort of thin regions. Okay, so I'll come to that. So you have this expansion. Now, what good is this expansion? Okay, so here is the main lemma. And then we'll use some further properties of Hermite polynomials. So till now, I've just used that they form an orthonormal basis, and I'll use something else soon. So here's the main lemma. Okay, so take any n in z plus the e. So you take any index in this expansion. Let en contained in E be the subset of edges E such that the corresponding index NE is positive. So note that NE is always a non-negative integer, so it can be 0 or non-zero. So you keep only those edges for which this is positive. Okay. So you just take that set. This defines a subgraph of lambda e. So you throw out some edges. You keep just the edges where NE is positive. Take any index. Then phi hat n is 0 unless there exists a path joining I and j in this subgraph. Okay. So this is the main input from the model. Now, I haven't used anything about the model yet, so or the fact that sigma hat is a ground state. So this is the thing that has all the material from the model coming in, the fact that sigma hat is a ground state. If you look at that function phi, which is the product of this ground state spins at I and j, and you look at this Fourier coefficients, you take the nth Fourier coefficient, where n is this one non-negative integer to each edge. So n defines a graph, a subgraph of the original lattice graph that you're considering, where you keep only those edges for which NE is positive. Then the Fourier coefficient is exactly 0, unless there is a path joining I and j in the subgraph. Okay. So let me first tell you how this helps. So what this tells you is that suppose I and j are far apart. Then you consider any term for which the Fourier coefficient is non-zero. It means there is a path joining I and j in the corresponding graph, which means that there are exactly, or at least a lot of them for which NE is positive. So the graph distance between I and j, at least those many terms have NE positive. So it's a product of a lot of univariate polynomials. So if I and j are far apart, then any Fourier coefficient, any Fourier term which contributes is a product of a large number of polynomials. Okay. And that is what gives it the instability. Okay. So it is sort of like the one-dimensional picture where you saw that the product of sigma I, sigma j is a product of a lot of signs. Okay. But here you don't have an exact formula, but you know it in principle from this thing, and then we'll see how to use this to get an estimate that that this is 0, unless there is a path joining I and j in this subgraph. Okay, any questions?
If you were to take a different distribution for Jij, but with somewhat similar properties for which you can find a somewhat similar orthonormal basis, would the lemma still apply?
I would guess so, yeah. I would guess so.
Symmetric, right?
What? It has to be symmetric, so it has to have some constraints, so it has to be symmetric. But yeah, so for example, if you take uniform between -1 and 1, you would have something like the Lagarde polynomials, or so you would have, yeah. So I didn't want to do it case by case. The next step it would be to have it in far greater generality, like a wide class of distributions. If somebody can prove that. But yeah, for specific things, yes, I think the same thing can be done. So we'll see one more property of why I'm specifically choosing the Hermite polynomials. So you can choose other bases, but there is a reason why I'm choosing Hermite polynomials here. Okay, but I'm running out of time. Okay, so let me now go through the proof of this lemma.
Sorry, what is that?
Yeah, yes. Yeah.
What is that plus? Is that plus is greater than or equal to 0?
Greater than or equal to 0, yeah.
Okay.
Yeah, greater than or equal to 0. Okay, so what's the proof of this lemma? So I and j are fixed, remember? Take any n. Suppose there does not exist a path joining I and j in En. Okay. Then there exists some A subset of lambda such that I belongs to A, J belongs to the complement of A, and NE equal to 0 for all E joining E and its complement. Okay? So if there is no path, then there is a contour which separates I and J in the subgraph. So you would be able to find the set A which contains I and its complement contains J, so that any edge which goes from I to J will not be in your graph, will have NE equal to 0. Okay? So let gamma equal to set of all such E which join A to A complement. Let's define a new environment, J prime of E equals JE if E is not in gamma, and JE minus of JE if E is in gamma. Okay, so you define a new environment where you just reverse the sign of every coupling on this gamma. So note that n is some fixed given number, and this gamma, there's nothing random about these things. Okay, so you're just taking one n. Okay. Okay. Okay, so what happens here is that phi hat of n, remember, is the expected value of phi of j times hn of j, but it must be also equal to expected value of phi of j prime, hn of j prime, because j prime is also a bunch of IIT Gaussian random variables. So when you take expectation, it shouldn't change, because j prime is also a collection of IID normal 0, 1 random variables, right? So if you plug in j prime instead of j, the expectation shouldn't change. Now, what is hn of j prime? Hn of j prime equals hn of j, since ne equals 0 for all E in gamma. So hn, the function hn, does not involve the JEs for E in gamma, right? So hn is not going to change. It's going to remain the same if we replace j by j prime. And finally, what is phi of j prime? Okay. So phi, remember, is a product of the ground state spins in I and j. Now, if you take here I and you take here j, and you take this contour and you are separating, so this is your gamma, and you reverse the sign of all these couplings, what happens is that the new ground state is just to flip everything inside. Okay, that gives the new ground state. So phi hat of j prime, phi of j prime is minus phi of j. This is the only place where I use that the function phi is a product of the ground state spins. So if you reverse the signs of everything along the contour, the new ground state is obtained just by flipping everything inside to have the opposite sign. Okay, you take the original ground state, flip everything inside, you get the new ground state. So you get this. So therefore, this thing is equal to minus phi j hn of j. So this tells you that phi hat n is minus phi hat n, which means that it's 0. So the Fourier coefficient is 0 if if n does not allow a path from I to j, if the index n. So you get that this coefficient is 0. Okay. Any questions about this?
Here you only use symmetry.
I just use, yes, so I use various things. I use the fact that this multivariate Hermite polynomials are products of univariate things. So that, yeah, but anyway, yeah, symmetry is the main thing that's being used here.
Just two things. One, the proof is brilliant. And two, you're actually not using absolutely anything about Hermite polynomials.
But I'm going to use it in the next step.
Awesome.
Yeah, in the next step. So what you get from here? Okay, so you have this. So now you remember that J, the new coupling is, I should give it some name. So the new coupling JE tilde is JE plus epsilon KE, where you have an independent Gaussian, but it doesn't matter if we also put in this factor because it's not going to change the ground state. If you scale the couplings by a constant factor, it's not going to change. So you can write it as e to the minus t JE plus square root of 1 minus e to the minus 2t KE, where e to the minus t is 1 over 1 plus epsilon squared. So roughly speaking, this means that t is roughly like epsilon squared over 2. So you take this t, which solves this equation, and you do the substitution. So there is a reason why I'm doing this. So here is the thing. So the Ornstein-Uhlenbeck semigroup on R to the D is the following. You take pt of f of x. So you have function f from R to the D to R. Pt f of x is the expected value of f of e to the minus tx plus square root of 1 minus e to the minus 2t z, where z is a standard Gaussian random vector. This is IID normal 0, 1 random vector. So if you define it like this, pt of f, this turns out this is a semigroup. pt plus s is pt times ps. And this is known as the Ornstein-Uhlenbeck semigroup. And the generator for this group, so Lf of x, which is the limit as t goes to 0, pt fx minus fx over t. This is the Laplacian of fx minus x dot, the gradient of fx. And and it turns out that the Hermite polynomials are eigenfunctions of this semigroup. So eigenfunctions of this generator. So if you take any n in z plus to the d, this is d. Okay. So if you take any n in z plus to the d, L of hn is minus n times hn, where this denotes the sum of the coordinates. Okay. And so this implies that pt of hn is e to the minus nt times hn, right? So if you take, expectation of sigma I hat, sigma j hat, sigma I prime hat, sigma j prime hat, so this becomes expectation of phi j, pt of phi j, okay? Because this is obtained by this, replacing by this thing, where t is defined by that equation. And so this is just sum over all n in z plus to the e of e to the minus the size of n times t, and then phi hat n squared, okay? And you know that phi hat n is 0 if the size of n is less than the distance between L1 distance between I and j. If the number of non-zero elements is less than this, then phi hat n must be 0. So therefore, this thing is less than or equal to e to the minus the distance between I and j times t times the sum over all n of phi hat n squared. And this thing is just expectation of phi j squared, which is 1. So you get that this product is less than e to the minus I times j times t, and t is epsilon squared. Okay, so that completes the proof. So I'll stop here and didn't have time to discuss open questions, but thank you.
Thank you for the lecture. I guess you teased us. So what are the questions that you wanted to
Oh, yeah. So the questions, there are many. So the main thing is to understand the spectrum. So I just proved some very basic thing that the coefficient is 0 unless, there is a path connecting I and J in the graph. So to understand this better, to understand whether a much smaller perturbation can give you chaos. And that is very important for solving the main open questions in the area, which is, again, I didn't have time to discuss, but, proving that, there are multiple infinite volume ground states. So it boils down to these questions. Also, if I and J are neighbors, that's a very interesting thing. If I and J are neighbors, then it's not chaotic. But if you look at the Fourier mass, whether there is some mass flowing off to infinity. Okay, so summation phi hat n squared is always 1. But if you look at all Fourier coefficients where some contribution is coming from some variable at distance bigger than r from the edge ij, and you look at that, and you look at the remainder, outside the region r. So consider the infinite volume system where you first send L to infinity. So you get some contributions from outside r. I can prove that the contribution is at least 1 over r, but the main question is whether it decays to 0 as r goes to infinity or remains bounded below by some positive constant as r goes to infinity. Okay, so it may happen that this product sigma I hat, sigma j hat, it will have some influence from nearby variables. There will be some significant influence, but whether there is a significant influence also from infinity. Okay, and that's a central question in this area, and so this chaos proves this conjecture, but it doesn't quite settle the question whether a spin glass phase appears or not. And understanding this spectrum, especially for neighboring I and J, understanding the spectrum whether all the contribution comes from a finite region or you have non-trivial contribution coming from infinity, that will settle the question whether this model at all has a spin glass phase, which has remained open. So it's supposed to be a realistic model for spin glass, but we don't know that it's actually a valid model.
Should be true already in dimension 2, because at some point you talked about that.
Exactly. So in dimension 2, they think it's not the case. It's almost certainly not the case. But in dimension 3, that's debatable. Also, the physicists believe in high enough dimension. Again, they say, okay, it should have a spin glass phase. It should be like a mean field model. So the question is more about dimension 3, 4, smaller dimensions like that.
So in dimension 2, you know that
no, nobody knows that.
Nobody knows anything, but you don't expect. Expect that
you don't expect the spin glass. Yeah. So you don't expect that. So generally, what I used is some very basic arguments and much more refined things in terms of these Fourier coefficients and how they behave. That would require that would be required to settle the question whether there is a spin glass phase or not. Okay, so that's the main question.
But it's mostly a question about the model, not the NL, right? It's
it's mostly a question about the model, but you can show it's mathematically equivalent to this understanding these Fourier coefficients. So I mean, I know I didn't write it down, but you can show that these two things are equivalent, and so it can be completely transformed into this sort of analytic question, analytic dominant real. I don't know exactly where it falls, but whatever works.
So do you also prove sensitivity to boundary conditions?
Sensitivity to boundary conditions, no, not in the paper, but I have to. I have to think about that. So I don't have that.
You expect it, right?
You expect it, yes. You expect it. Although
Maybe
not in 2 dimensions.
Yeah, you have to be in higher dimensions.
In higher dimensions. So there will be some fundamental difference between sensitivity to boundary conditions, sensitivity to perturbations of the couplings. Yes.
Do people at all care about the case where your spins are not like plus or minus 1 value, but maybe take values in the 3-dimensional sphere?
Yeah. We're just discussing that in the during lunch.
Okay.
So those are supposed to be harder than the plus minus 1 case.
This final part, I was trying to understand it, but I have no idea currently. So, in the final part, when you're using the semi-group link to the Gaussian measure, one could, in general, repeat the whole construction for any measure which is
Yes.
decaying fast enough and symmetric fast enough.
Yes, you just have to have an orthonormal basis of eigenfunctions for a generator.
And what I cannot understand here, it's would everything work?
That's to be seen. I didn't verify. I would expect it to work. But I cannot for sure say it unless not verifying. But once you have a good eigenfunction series for a suitable generator, should be good.
If you have a small magnetic field, this proof doesn't work.
No.
But is there still supposed to be sensitivity?
If you have a small magnetic field, I think in the lunch that we were having in this Phil Anderson.
Yeah.
So I think David Huse was saying that, or Daniel Fisher was saying that maybe not. With any small h, maybe you don't.
Maybe it's not true anymore.
Yeah. But it's not. Again, we don't know how to do that.
What's the Hamiltonian if you have a magnetic field?
Oh, then you have just plus h times summation sigma I, some constant summation sigma.
But if the field is also independent Gaussian,
Yeah, that'll be more complicated, I think. But yeah, so the question is if the field strength is small enough. So if the field strength is large enough, then that will dominate, and you can prove that it's essentially.
yeah, but it looks like your argument about symmetry will work still.
Yes, that is true. Although, yeah, that is true. But if it's Gaussian and independent of the GIJs, then you can replace maybe the spins by spin times the sine of GI, and then you would have a positive external field together with an Edwards-Anderson part. Yes.
Is this also work for a local minima of the Hamiltonian, or does it have to be a global minimum?
As written, it has to be a global minimum. So first of all, the sigma I, sigma j has to be well defined as a function of the couplings for this whole argument to go through. So just the fact that it's a global minimum and it's well defined up to a global sign change, that ensures that it is indeed a function. So if you don't have a function, then you have to somehow choose one local minimum, and you need to have a rule which.
The second best?
Second best, I don't know if it will have this property that if you flip a whole contour, all the j's, then the thing inside is going to flip. So that's not clear. Maybe that's true. So I have to think about that. Yeah.
I think that at least the way you stated it holds, right?
Well, you have to say what you mean by second best, like second best just in terms of value, or second best among everything that's orthogonal to the original one, like you do in eigenvectors. So that's that you have to, because you can get a second best just by changing one little thing somewhere, right? See.
Okay, if there are no further questions.